Okay, so before we are going to the regular presentation, what do you mean by a system? The system is a group of components connected together to perform a specific task. Okay, so which means you people have gathered in ECE. The specific task is to get the bachelor degree in electronics and communication engineering. But what do you mean by control system? Which means you have some control parameters like your class advisor, your HOD, your dean, like that. You have certain administrative roles. No. What is the purpose of those roles? Those people will work for you in order to make you to reach your aim. What is your aim? To get the degree in electronics and communication engineering. Okay. Likewise, system is classroom. And control system means the classroom with the controller, so-called faculties, HODs, deans, and the administrative roles, whatever you want to role, you want to have, you can have. Right? So that is the difference between system and control system. And again, coming to control system, we have two major categories, namely open loop system and closed loop system. Right? What do you mean by open loop system and what do you mean by closed loop system?
Sir, open loop system, we can say in layman language, is a system
Yes?
without feedback.
Open loop system without feedback. Closed loop means?
With feedback.
Okay, good, good. So open loop system means we people are there, we are acting as a control system. We'll give the lectures and we will evaluate your paper and we are giving marks to you. That is what your open loop system. Plus closed loop system means based upon the marks you have obtained. Actually, our aim is to get the pass mark. But if you are getting less than pass mark, in our institution we are having 50 as a pass mark. So 50 is my aim. If some X student or Y student is getting 40, 45 marks, what is the difference? Some 10 marks means why he has got failed, why he has got less than 10 marks, and what the action I can take on him in order to bridge the gap. So that is the role of a controller. So based upon the feedback, if you are acting, that is called closed loop control system. Open loop control system means we don't have any parameters, we don't have any feedback, just we will give the input, we will observe the output, and we will change the mode of control, that's all. Okay, so practically if we are saying our traffic light control system is a open loop system, do you all agree with me? Because the purpose of traffic light control is to reduce the traffic in the signals. But what we are actually doing, we are not taking the human density anywhere, just we will openly give 1 minute for all the roads, right? If you are giving 60 minutes, 60 seconds or 30 seconds for a particular road, some other side we may have large people. So density may be increased. What is my ultimate aim? To reduce the people density. But because of our poor control actions, there may be density increased. Which means we are taking some control actions, but not based upon the feedback. So traffic light control system is a good control system, example of open loop control system. Okay. So we have studied system and we have come to control system. In control system, we have classified two types, open loop system and closed loop system. So wherever you take control actions, there is a role for control actions, controller, right? So what are the types of controller? That is what we are going to study in this session. First, we have discussed need for controllers. Whatever the control action we want to take, that controller will play the role. What control action I have to take and how can I make the system to reach the set point? All those responsibilities lies with this controller. Okay. Then types of controller we have come. Types of controller, elementarily they have started with on-off controller. Then we have migrated to proportional controller, integral controller, derivative controller. And in this, proportional composite mode is also possible. Proportional plus integral, proportional plus derivative, proportional plus integral plus derivative. So all these combinations are possible. Then controller tuning method means, see, if you are having a particular type of controller, what gain value we should have, and depending upon the gain value, how can we design the controller? So those things will be taken care by the Ziegler-Nicholas and Cohen and Kuhn method. these two persons will take a what gain value we should have in order to make the system to reach the set point. So there are two methods, Ziegler-Nicholas and Cohen and Kuhn. Need for controller, this I have discussed with you. Reference input, error, controller, control signal, whatever the error we are having, that error will be given to the controller. This controller will decide what control action we can take. That will be your control signal, and this control signal will be given to the controlled plant. And here, final control element will be there. Final control element is the person, he's the responsible person to get the command signal from the controller, which means your control signal, and it will take the order from the controller and it will execute the order of controller. So whatever been decided by the controller, this final control element will execute that, and that output will be taken as feedback in order to compare with the set point. So our controller plays the crucial role. What control action has to be taken, that will be decided by this controller. An on-off controller. See, on-off controller means we have only two options, either 0 or we may take 1. Example is water heating. We will insert the heater. That heater will produce the heat in order to increase the temperature, right? If we want to reduce the temperature, just we can take that outside. We cannot decide what amount of heat has to be given outside, which means either we can give 100% heat to the water, or we should not give the heat to the water. Only two things may happen. Boolean, either 0 or 1. So this control action U of t will be taken U1 if it is 0, less than 0, error is less than 0. U2 if error is greater than 0. That's all. Only two possibilities. If we want to increase the water temperature, we'll immerse the heater. If we want to reduce, I have to remove that entirely. We cannot give 50% heat. We cannot give 60% heat. Like that we cannot give. So only 0 or 100%. On-off controller examples. See the same example. The temperature of the temperature in a tank is to be controlled by two position controllers. When there is a heater, when the heater is off, the temperature drops at 2 Kelvin per minute. See, if we are switching off the heater, which means we will not disseminate any heat, means per minute 2 Kelvin will be reduced inside water. Okay. If the heat is on, which means if you are giving supply to the heater, it will start to give the heat to the water. That means 4 Kelvin per minute will be increased. For 1 minute of time, 4 Kelvin will be increased. I want to make the set point is 323 degree Kelvin, and the neutral zone is 4% of the set point. Neutral zone means if 323 is the with 4%. So 104, 320 means almost 12%. Plus or minus 12 will be permitted. That within that time it can swing. Okay, and there is a 0.5 minute lag at both the on and off switch points. Find the period of oscillation and plot the water temperature versus time. See, 0.5 minute lag time means if you are initially switching on the heater, it will not produce the heat immediately and it will not be experienced by the water immediately. Definitely there will be lag time, and that lag time is 0.5 minute, which means 30 seconds. So they have asked us to find the period of oscillation and plot the water temperature versus time graph. Okay. So what we can do here, we can we can give the heater here and water inflow, water outflow. We are measuring the temperature of the outlet water, and that is been given to the controller. And these people will decide stream wave, whether we can give input or not. They are not directly giving the heat, just by means of sending the steam, they are increasing the temperature or decreasing the temperature. They are not directly giving the heat with the help of heater, right? That will be controlled by the steam supply. Steam means heated water. So I am sending heated water inside or heated gas inside, and that will give the temperature or heat to the water. Steam supply will be controlled by this heater. So we are switching on the heater or switching off the heater. That will affect the steam supply, right? And that temperature will be controlled, and that will control the temperature of the water. Okay. Now, what is actually decided? 323 it has to be decided, right? Plus or minus 12 Kelvin is permitted, almost 12 Kelvin, not exactly 12. 12 Kelvin is permitted. So 13 Kelvin they have decided, 310, and here it is 335. Within this swing, it is swinging. So it is when I am switching off the heater, what will happen? Per minute, 2 Kelvin will be reduced. So here I am standing, I am switching off the heater. Now the temperature is slowly started to decrease. It is coming to this point. And once it is beyond the controllable limit, it is beyond the acceptable limit, which means your neutral zone. Again, my controller will give control action to the heater. You switch on the heat. So what will happen? It will start to increase the temperature. So it is slowly increasing. It is increasing. And whenever it is crossing the upper set point, which means it is crossing the neutral zone value, what will happen? It has to reduce the temperature, because my ultimate aim is to maintain within 320, exactly 323 degree. But exactly maintaining 323 is not possible. So what I'm doing, I'm introducing a neutral zone, and with that neutral zone, my temperature has to be swinging between these two temperature levels, which means almost 310 and 335. Within these two limits, it has to be swing. So if it is beyond 325, what the temperature is being measured, and what control action will be taken by the controller? You switch off the heater so that the temperature will be reduced. Again, the temperature is started to reduce. Again, it is starting increasing. Depending upon the control action, it will all on off, and similarly, the temperature will be increased or decreased. Okay, well, so just by on and offing the final control element, we can control the required parameter. This is called on-off controller. See in the question, not the water temperature versus time curve that I have done here. What is the previous question? Find the period of oscillation. So period of oscillation means complete cycle. How much time it is taken to complete one cycle? See, it is started from 323 here. It is coming to negative. It is going to positive peak, and again it is coming to 0. So how much time it has taken to complete a single cycle? Say, what do you mean by cycle? It comprises of both positive and negative peaks. So here it is started. It has come to negative peak. It has gone to positive peak. Again, it has come to the place where it started the journey. Yes, what is the period of oscillation?
21 minutes.
Yes?
21 minutes.
Yes, approximately 21 minutes. It is between 20 and 25. So approximately it is 21 minutes. So to complete a cycle, they have taken 21 minutes. So what is the drawback you feel with this on-off controller?
So we cannot keep the temperature at a specific point.
Yes, good. Then?
Sir, we cannot get the desired output.
Yes, good. Then, see, we cannot have the exact set point. We cannot reach the exact set value. Definitely, it will be swinging between two particular values around the set point. We cannot exactly get what we require. So that is the drawback of this on-off controller. So we are moving to a next type of controller called proportional controller, integral controller, and derivative controllers. Okay. Proportional controller. From the name itself, we can understand that proportional. It will take the control action proportional to the error value. See, go back to the diagram. See, this is your controller. This controller will take control action proportional to the error value, because error is the input to the controller. What is the responsibility of the controller? It has to give the control signal or command signal. This command signal or control signal will be directly proportional to the error value. So what is the necessary to give control action proportional to the error. See, from the slide itself, we can say why proportional mode is required. The famous example, if you are writing a C programming or C++ programming, if you are missing a single semicolon, what will happen? Your entire program may be correct. If you are missing a single semicolon, what will happen?
So syntax error will occur.
Syntax error will occur. You cannot run the entire program, right? You will not get the output. There is a small problem. There is a small error, but that will give you a big problem. So what my proportional control will do is it will magnify the error. So naturally, I will explain with my students with the example. If a student is doing a small mistake, if X faculty is not giving emphasis to that particular mistake, what will happen? The student will think that, hey, this faculty is not noticing my mistakes, so I can work as per my wish. I can do as per my wish. I don't need to consider this particular person. Like that, he will decide and he will work about whatever there is in his mind. But if a particular faculty is magnifying his mistakes, if he is amplifying his mistake, what a student will think? No. We should not have any blunder mistakes with this particular faculty. If we are doing, he will find out what is the mistake and he will magnify the mistake. He will spoil our name. So we should not have any trouble with this faculty. Like that, students will think, right? In a very similar manner, proportional controller will act. Always the transfer function is defined as the ratio between or ratio of Laplace transform of output to the Laplace transform of input with zero initial condition. That will be the proper definition for transfer function. So please keep this in your mind. Always transfer function will hold for zero initial conditions. It will not be working for the initial conditions. It should have only the zero initial conditions. If at all only we can apply the transfer function concept. If there is no initial condition, if there is no zero initial condition, definitely we cannot hold the transfer function for that particular system. So here I'm taking Laplace transform on both sides. For controller, you can go back to the controller design. For controller, what is my input? Error. And what is my output? That is control signal. So what is the transfer function of a controller? Laplace transform of output to the Laplace transform of input. I am notating U as my control signal and E as my error signal. So E is my input and U is my output. Okay. So Laplace transform of output to the Laplace transform of input with zero initial condition means E of S divided by E of S. That is what I have taken here. E of S by E of S is equal to Kp. So I am introducing a Kp here. That is what your controller. In place of controller, I am giving the Kp. So what it will do, Kp is a simple gain, some 5, 10, whatever the value, depending upon the problem. So it will multiply my error and it will produce the control action. Error, it will magnify the error and it will give command signal to the final control element. Coming to integral controller. So integral controller means this controller produces the output proportional to the integration of the input. It is not directly proportional. It will integrate the error and give the output. See, again I am emphasizing error is my input. Error is nothing but it is the difference between actuals and desire. Okay. My control action is directly proportional to E of t dt. What do you mean by integration? So integrating means we are accumulating, we are adding, right? Which means my integral controller will not take the present error. What it will do means it will track the entire history. What is the error at 0 time and what is the error now? Put together, what is the error? It is not taking only with respect to this time. It is taking for the past values also. From 0th instant to present instant, what is the value? It will not consider the present value. It will not take the present. If you are taking for the nth time, up starting from 0 to n minus 1, what is the error? That it will take. Okay, it will work on the history, which means It is also like a faculty. What a faculty will do, if a faculty is working on the present mistake what you have done, that faculty is proportional controller. If you commit a mistake and if you are caught by a faculty, if that faculty is taking the history of yours, what mistake you have done in the first day and what you have done with the last day till date, what error, what mistake you have committed, and depending upon the entire history of the mistakes what you have done, if you are punishing him, that is called integral controller. He will not take the present mistake. He will take the entire mistake, starting from day one college to till now. So that is what integration. Integration means past history. If you are taking the entire history of the error. So U of t is directly proportional to the integral of the E of t. If we want to remove this proportional symbol and if we want to introduce the equivalent symbol, we have to introduce a proportional constant called Ki. K stands for integral gain. It is U of t is equal to K into integral U of t dt. Again, same logic, I am taking the Laplace transform on both sides. Now this becomes U of s is equal to Ki into E of s divided by S. What is Laplace transform of output by Laplace transform input, which is nothing but your transfer function. Here it is U of s by E of s is equal to Ki divided by S, because integration means it is 1 by S. If you are taking integration, if you are taking Laplace transform for the integration, that is nothing but 1 by S. So my transformation becomes Ki divided by S. So in the place of controller, I am having Ki by S. See, here I have only Kp, but here I am having Ki by S because of the integral action. Okay, proportional we have studied, integral we have studied. So proportional you can keep as in the present value alone. What is the error present? What is the error now? It will take control action. But integral means it will not consider the present value. It will take the entire past history. That is what your integral controller. So obviously we have one more controller called derivative. So my derivative controller will work on the future value. It will not consider the past. It will not consider the present value. It will focus on future alone. What stage we are now, that it will not think. It will think what we may be at 10th second, what will be at 20th second, what we will be at 30th second. It will focus only on the future. My output control signal is directly proportional to the derivative of the error. If we want to remove the derivative, the proportional constant, we have to introduce the equal value symbol with the constant introduction called Kd. Kd stands for derivative gain. If you are taking Laplace transform on both sides, you will get U of s is equal to Kd into S into E of s. So my transfer function becomes U of s by E of s is equal to Kd into S. See, proportional will work on the present value, integral will work on the past value, and derivative will work on the future value. A single mode controller cannot hold a good control action. It will need the combination of all the people. It is a teamwork. So that is what PI, PD, and PID controllers. From the name itself, we can say P means present value. So leave that. PI means what is the combination?
Proportional and integral.
A proportional integral, okay, but what values it is taking? It is taking present value alone, it is taking future value alone, it is taking past value alone. What it is doing? Proportional plus integral means?
Past and present.
Yes, past and present. Now you think, if you know about past mistakes, what I have done and what I can do now. If you are thinking, will you shine? Is it possible? Up to a certain extent, PI. But I know the present and future. Which will hold good, PI or PD? PI means present and past. PD means present and future. See, based upon our previous things, we can decide what we can do. But PD means I don't know the history. I don't know anything about me. Just I want to focus the future. Is it possible? So compare with PI, PD holds good. But PD is not widely used because just focusing on the future without any past history, it will not be effective, it will not be giving good predictions. Whereas PID means here I know the present value, I know the past value, and I can able to predict the future. So this will hold good. Practically, we are using proportional plus integral plus derivative, these three things widely. Okay. Some extents we are using integral alone, some cases. In some cases, we are using P plus D. That is also possible. Whereas derivative controller cannot be used alone. Because derivative means focusing the future, right? Focus in the future without any data. I don't know about the present situation. I don't know about the past history. Just if I want to focus on the future, it is not possible. It is not feasible. So, derivative controller cannot be used alone. This is logical answering. If you are coming to the mathematical view, derivative controller means KD into derivative of error with respect to time. Say for example, my steady state error, E means error. If I am reaching a error at constant value, say I want to reach the temperature as 100 degrees Celsius, right? It is reached 60 degrees Celsius. And after 60 degrees Celsius, it is not going beyond the 60 degree. What is the error? See, 100 is my aim, but it is settled at 60 degree. What is the error? 40 is my error. It is saturated. See, in our words, dE by dt means what is the meaning? Can you claim this as rate of change of error? dE by dt. Literally, can you accept derivative of error is nothing but rate of change?
Yes,
Yes.
sir.
Yes. See, rate of change is nothing but derivative. Error is constantly 40. What is the rate of change?
0.
0. So error is there as 40, but control action is producing 0. What will happen? There will not be any control actions. So the entire system will be collapsed. So derivative control cannot be used alone. So logically, if you are talking about that, it is not possible to focus the future without the data of present and past. So derivative control cannot be used alone. If you are talking with respect to maths, so derivative control is nothing but rate of change of error. If the error is constant, rate of change of error will be 0. So rate of change 0 means here dE by dt is 0. What will happen? The entire right hand side will become 0. There will not be any control actions. So the system may be collapsed. Hence, derivative controller is not used alone. This is a famous 2-mark question we used to ask to the students. Okay, why derivative control cannot be used alone? Logically, if you are saying because of the focusing on the future value alone. Mathematically, if you are saying it is rate of change, if the constant error is there, rate of change will be 0. So no control action will be performed. Okay, if you are coming with this, PID is the first controller which holds good. Below PID you will have PI. Below PI you will have P. Below P you will have PD. Below PD you will have I. And derivative is the bottommost one which cannot be used anywhere. See, before moving to the response, I can show you an experiment what we have conducted in our laboratory through MATLAB software. See, in Word file, I am studying the effect of PI and PID controllers on time response. The system what I have chosen is armature control DC servo motor. See, this is the example, classic example we are choosing usually, which means your system has been taken here. You consider this DC motor as a system. Don't go beyond that. And you will be having amplifier gain and you will be having error gain. Okay. This is a system. And system parameters I have chosen. What is KP, what is KD, what's the armature resistance, all those things I have taken. And PD controller mode is for your knowledge. What is the response I am getting? That is what more emphasis here. See, my transfer function is KT divided by JS plus F into R plus LS in plus KB into KD. This is what my system, what I have chosen. In my laboratory, I have chosen this as a DC servo motor. This may be any system. For example, I have chosen the DC servo motor. Okay. So K is my error gain and K is my amplifier gain. This is my open loop transfer function. And response without controllers. We don't have any controller. We don't have any control action, right? And my error is taken as error gain is 5 and amplifier gain is 1. And this is what my transfer function I have calculated. You may ask the question that you are having these much letters, sir. How can you arrive this value? Means by conducting the experiments, I have got these values. What is the armature torque constant, back EMF constant, armature resistance, inductance, these things. I have conducted the experiment and got the values in my laboratory. Okay, that is what I have fitted with this transfer function and I got this value. This is what my response without any controller. I don't have any controller here. So first we have to declare numerator and then denominator. We will get the system. So system is equal to transfer function of numerator comma denominator. And for that system, I have plotted the pole zero plot, right? And I have taken the step response. This is open loop system alone. We will not consider any other things. We are considering the system alone. We are giving input and we are getting the output without any controllers. Okay. Next one, closed loop without controller. That is open loop system. Here, closed loop system, I am bringing the feedback with the gain is 1, unity feedback, which means at this junction, I am introducing these two values. Open loop means only this system, 0.1 divided by 0.01 s square plus 0.414 s plus 0.41. I am giving input and will get the output. Feedback means without any controller, just I am taking the feedback and I am giving with this Ka and Ke alone. So I am making the feedback series of system comma 5 and I am taking the feedback for the system with unity feedback. One stands for unity. And for that system, I am taking pole zero plot and I am getting the step response. These things we have to put in the matter. Just I want to use out. See, open loop system response without any controller. I am not introducing any controller, just a response. My ultimate aim is to meet at 1. That is what unity. Step input only I am going to give. If I am giving 1 as input without any controller, without any feedback, I am getting 0.22 or 0.23 as my output. Okay. So error is huge, almost 0.8. 80% error is there. Then I am bringing the closed loop system and it is trying to reach almost 0.6, not exactly 0.6, 0.58, like that it is reaching. So here also I am getting almost 40% error. So first system is open loop, there I am getting 80% error. Then second system is closed loop without any control action. So that is almost 40% error is there. Okay. So what I am going to do at next level, I am introducing a proportional controller with the gain of 10. So I am introducing a gain called 10. Same logic, series of system with 50. Why I am introducing 50? 5 into 10, this can be multiplied. So 50 and in series with the system, 0.1 and divided by 0.01 s square plus 0.14 s plus 0.4. And this is fed back with the gain 1. So unity feedback. And for that also I have plotted the pole zero map and I am taking the step response. Now you can observe the results. You can see in the graph, closed loop response with input control, it is reaching almost 0.2 and if you are taking the response, it is reaching almost 0.1. Still there is a gap. Still there is a scope for improvement. So again, I'm introducing a integral controller 5 by s. You know, K divided by s is the transfer function for the integral controller. So it is 5 by s. Again, I'm calling numerator, denominator, and it is in series. And I am taking the feedback. And now I can see the results. See, it is reaching the 0.1, but it is reaching the 1, but it is giving overshoot than that of the previous case. So I'll read out the observations then and there. Without any controller, what is the observation? In open loop system, the response doesn't reach the final value exactly. It is going. But in closed loop system, it is reaching the set point, but steady state error is reduced. See, here we are having 80. First case we are having 80. For the second case, we are having 40%. So in order to reduce further, I am introducing proportional controller. What is the output of the proportional controller? Proportional controller is overshoot and oscillations. So most of the time it is not introducing. For this case, it is producing the overshoot. But definitely it will produce oscillation. See, rather than this, compare with the previous two values, the steady state error is further decreased. Again, I am introducing the proportion plus integral. PI eliminates the steady state error. Almost it nullifies to 0, which means 0.98, 0.97, like that it will take. But overshoot is maximum compared with the previous case. Overshoot means this peak overshoot. Okay. So to reduce the overshoot, okay, sir, what is the necessity to reduce the overshoot? Can anybody say? Why I have to reduce the overshoot? Let it go. So you think about the valve control. If I am giving the control action P plus I, it is moving to the high peak. Think about the mechanical assembly. If you're going high peak, what will happen? See, there are two mechanical materials. Say, for example, there is one valve. In that valve, you are having the position. If that position is going highest peak and it is coming down, going peak, coming down, sudden movement of positive to negative, what will happen to the mechanical arrangement? Whether friction will be more or not, whether damage will be more or not.
Yes, sir, there will be more damage.
Yes, because of sudden increment and decrement. So it will cause the damage to the particular system. So overshoot has to be reduced. Overshoot has to be reduced. For that, I am introducing the derivative controller. Okay. Right. Again, 50S is introduced. So the same procedure I have done. And I have got the output. It is reaching the set point without any overshoot. But problem is settling time will be increased. So settling time is reduced means it is literally it is not reduced. It is increased actually. If you are introducing derivative, what will happen means it will introduce a sluggishness. If I want to focus on the future, definitely there will be a time lag. Okay, so the sluggishness will be there. That is the drawback of PID controller. See, let me narrate the drawbacks of the controllers sequentially. Proportional means it will reduce the steady state error, but still there is a large steady state error possibility to reduce. Then proportional plus integral means steady state error will be reduced, but there is an overshoot. Okay, and if I am introducing proportional plus integral plus derivative, my overshoot is nullified, but the problem is there is a slight time delay in order to reach the settling time. See, first with P controller means it is blue color. See, the blue color is having like this. It is almost reaching. It is in 100. Okay, and my aim is to not to maintain at 100. It is to maintain at somewhere 120. Okay, and I am introducing PI. PI means it is giving overshoot and it is getting settled down at the same value. So to reduce the overshoot, I am introducing PID. Red color. What has happened? The overshoot reduced, but still there is a scope for improvement. Okay, overshoot is reduced and it is reaching the set point after the green color. So it will be more clarified with this slide. Without control action, it is going. We need not to say about the set point. If I am introducing P, the error is reduced. I am introducing PI, overshoot is there, but it is reaching the set point. And PID means it is reducing the peak overshoot, but it will take the time to reach the set point. P will be fast, which means P will be more faster, and compared with P, PA will be less fast. PID it is sluggish. Slow response will be there. Okay. So that is what I have tabulated here. I am introducing KP means it will decrease the rise time. it will increase the overshoot. Settling time, there is a small change. Steady state error will be decreased. For open loop system or closed loop system, if I am introducing a proportional controller, rise time will be decreased, overshoot will be increased, settling time will be, there is a small change in the settling time, but steady state error, drastic change in the steady state error. If I am introducing KI, it decrease the settling time, decrease the rise time, it increase the overshoot. Settling time initially decreases, but it is increasing. Steady state error will be eliminated. If I am introducing KD, this time, overshoot is almost reduced. Settling time is also decreased. Steady state error, there is a small change in the steady state error. This is the effect of PPI and PID controllers. Next, applications. Where we can use the applications. P, as I told you, P means present, eliminates the present error value alone. When to use? System with slow responses. System tolerant to offset. There is some offset. If the offset is not having much emphasis, we can use the P controller alone. Examples are float valves, thermostats, and humidity stats. Okay. Integral means it eliminates the history of the error. Not often used alone. Separately, it is not used alone, as it is too slow, because we are taking the entire history. Okay, it is used for noisy systems. And D controller means it focuses on the future, it forward. It is not separately used because it is too sensitive to noise and does not have the set point, which means it not have the sensitivity to the set point rather than the noise. As I already told you, derivative controller cannot be used alone. The logic, why? Because rate of change error has been calculated. If the error is constant, rate of change of error will be 0, so it cannot be used anywhere alone. Okay. Next one, P plus I, present plus back, often used, thermostats, flow control, and pressure control. Whereas PID means it is calculating all, it is taking all. It is often used, it is more robust, but can be noise sensitive. Cases where the system has inertia that could get out of hand, which means temperature and concentration measurements, will use this PID combination.